Alright guys, welcome to this page of the notes, and here's what we're going to do. Now we're going to really start to have some fun with matrices. Our first objective or learning target was knowing how to add and subtract matrices. And that's what we're going to start talking about here. How do you go about adding or subtracting matrices? So let's jump right into it, and we're going to start with addition. What I've got for you here is a great little definition for adding and subtracting matrices. Addition is defined only for matrices with the same dimensions, all right? So what that means is in order to add matrices, you must have matrices with the same dimensions. If the matrices don't have the same dimensions, you cannot add them together. In fact, what we'll say is that addition is undefined, all right? So if I ever ask you on a test or a quiz or in the homework or wherever, even in the notes here, if I ask you to add two matrices and the dimensions are not the same, you'll just simply put undefined. Addition for those matrices is undefined. It's not possible. But as long as the dimensions are the same, we can do matrix addition. And I know that this looks really scary. It's not. Let me walk you through it. What you're going to do is to add two such matrices. We add the corresponding elements of the two matrices. So here's what I've got. I have a 2 by 2 matrix. I have a 2 by 2 matrix. Because the dimensions are the same. Oh, sorry, that is my highlighter. Hold up. 2 by 2. 2 by 2. Because the dimensions are the same in these matrices, I can add these matrices together. And how do I do that? Well, it's just this simple. Take the element in the first position, add it to the element in the first position, I get my new element in the first position. So whatever A is, add it to whatever E is, and that's your new element in your sum matrix. Great. Take the element in the second position, right, corresponding positions, add them together, that's the element in the second position of your sum matrix. I think you're starting to see the pattern. Third position, add them together. Fourth position, add them together. And now you can see why the dimensions have to be the same. If the dimensions aren't the same, you're going to have elements in one matrix that don't have a corresponding position in the second matrix. And we add elements in corresponding positions. If it doesn't have a corresponding element, you can't add it to anything and the addition process falls apart. So you must have matrices that are the same dimensions. We add corresponding elements, and let's go ahead and practice. I have right here an example one for you. I give you two matrices. You first must determine, is addition defined for these matrices? Do they have the same? Can I even do it? Can I do addition? Well, in this case, what I've got here is I have a 2 by 3 matrix. 2 by 3. And this one is also a 2 by 3, so yes, addition will be defined. Let's go ahead and do it. 4 plus 5 is going to be 9. 0 plus a -1 would be -1. 3 plus 2 would be 5. 1 plus 0 is 1. -2 plus 3 would be a +1. And -4 plus a -5 would be -9. What I have just done is I have found my sum matrix. Right? This represents my sum matrix. Not bad, right? Yeah, piece of cake. Let's take a look at the subtraction. Maybe that'll be trickier. All right, well, here's the way subtraction works. Subtraction is also defined only for matrices with the same dimensions, and to subtract two such matrices, you will subtract the corresponding elements in both matrices. So it sounds like subtraction works the exact same way as addition. As long as the dimensions are the same, subtract corresponding elements, and you've got your difference matrix. That's exactly the way it works. If you take a look here, I happen to give you a 2 by 2 and a 2 by 2. And you just subtract corresponding elements. First position minus first position, you get your first element in your difference matrix. Second position, second position, second position in my different matrix. C minus G, D minus H, right through just like you do addition. Great, let's give it a shot. So here we go. I have an example problem for you here. First, we need to make sure that subtraction is defined. If my dimensions aren't the same, then subtraction would be undefined, and we just would say, well, I can't subtract these matrices, it is undefined, but we don't know that. Let's find out. So what I've got here is a, let's see, rows, then columns. It looks like I got a 3 by 2. Again, rows by columns, looks like I got a 3 by 2. So subtraction's gonna work. Now all you have to do is subtract corresponding elements. 3 minus 6, I think that's a minus 3, double check my math, but I'm pretty sure. 2 minus 0, that's just gonna leave me with a 2. 4 minus a minus 5, careful, you've got a double negative, so you'll add a line, change the sign, it'll actually be 4 plus 5, how about a 9? Negative 1 minus 6, so what I'm going to have here is a negative 1 minus 6 should give me minus 7. 0 minus 2, how about a negative 2? 6 minus a negative 1, double negative, add a line, change the sign, so it would now be 6 plus 1, I get another 7. Put that guy inside brackets, you just found your difference matrix. Well, so far, I'm feeling pretty good about this, right? Addition was fairly easy. Subtraction is pretty easy. We'll do a couple more problems here in a second just to make sure that you've got the hang of it. But there was a second objective. I asked you guys or told you guys that you would need to be able to do what we call scalar multiplication. Well, let's take a look at that. What I've got for you here is a definition for scalar multiplication. Let me go ahead and highlight a few things for you so you know what it is. To form a scalar product, multiply each element in the matrix by a scalar. Now, a scalar is just a fancy word for a number. All right, here's what I mean. What we're going to do is you're going to take a matrix. In fact, we'll take this matrix as our example. I want you to multiply the matrix by a 2. Well, here's what's going to happen. If I multiply each of these numbers by 2, what have I done to the matrix? Well, I've doubled every element, right? I went from this being a 2 to now being a 4. The matrix has doubled. I have scaled it by a factor of 2. That's why we call this constant a scalar. It's going to change the magnitude of each of the elements in my matrix by whatever that number is. So in this case, 2 times 2 would be 4. Apologize, that's my highlighter again. 2 times 2 would be 4. 2 times a negative 1, negative 2. 2 times a 4 would be 8. 2 times 3, 6. 2 times 0 is 0, and 2 times 1 would be 2. And what I've got here is my scalar product. I have a matrix where the magnitude of each of the elements is twice as big as it used to be. It has been scaled by a factor of 2. That's why we call it scalar multiplication. You're just going to be multiplying every element in the matrix by a number, by a scalar. All right, a couple of things for you guys here before we jump into doing some extra problems, and it is this. I just want to talk about a couple of the properties of matrices. So if you think back to chapter 1 where we were talking about the properties of real numbers, we had a bunch of properties. In fact, some of them are listed here. There was the commutative property, the associative property, the distributive property, and several others. I want to talk about these 3 in particular, and here's the reason why. If you remember back to the commutative property for real numbers, we had the commutative property of addition and the commutative property of multiplication. And here's what they said. You can take any 2 real numbers, any real numbers that you can possibly think of, and the order of addition doesn't matter, right? 7 plus 4 or 4 plus 7, well, it equals 11 either way, right? And if I did multiplication, any two real numbers, if I multiply them together, the order of multiplication doesn't matter. 3 times 2, 2 times 3, both of those are equal to 6. Order doesn't matter. Okay, well, we actually have a commutative property for matrices, but I need you guys to be careful. We only have a commutative property for matrix addition. There is no commutative property for matrix multiplication. In fact, I know it's a little weird to think about right now, but when we get to matrix multiplication, I promise I'll remind you of this and I'll show you why. I'll even show you an example. But it turns out for matrices, order matters when it comes to multiplication. In fact, we're going to look at an example where in one order I can multiply the matrices. If I did A times B, matrix multiplication works. If I flip the order and try to do B times A, turns out matrix multiplication is undefined. I know that seems really weird. I promise it'll make a lot more sense when we actually get to matrix multiplication. But for now, commutative property for matrices, only addition. It is only the commutative property of addition for matrices. Likewise, when it comes to the associative property, for real numbers, we have the associative property of addition, the associative property of multiplication. Well, for the exact same reason we just talked about up here, when it comes to matrices and multiplication, order matters. The order matters. So therefore, we only have an associative property for addition when it comes to matrices, right? It doesn't matter how you group the matrices together. As long as you're adding them, you're going to get the same answer, just like for addition. Doesn't matter what order you add the matrices in, you're going to get the same answer. Not true for multiplication. Not true for multiplication. The distributive property. The distributive property will also work for matrices just like it did for real numbers. And here's the reason why. If I did A plus B times K, that would be exactly the same as K times A plus K times B. You say, well, hang on a second. I thought that order mattered when doing multiplication. When doing multiplication of matrices, yes. But this is a lowercase k, which means it is not a matrix. It is, in fact, a scalar, right? When you're multiplying a matrix by a number, order doesn't matter. You can add them together first and then multiply by the scalar, or you can multiply each matrix by the scalar and then add them together. Perfectly fine. If these were a matrix, right, if this were a matrix, then yes, we'd have to be much more careful about the order in which we do it. But for scalars, distributive property certainly will work. So, if we head on over to the next page of the notes, we'll try a few more problems involving matrices, and I'll meet you guys there.